So welcome. We're doing Gauss's law. This is the second video on Gauss's law. We're part of the way through it. We developed this idea of flux, and you can picture flux as the number of arrows you have going through an area. And the flux, you get it by multiplying the electric field strength by the area. And you can figure out how much flux you have. And so what happens if the area, remember this is an imaginary area. We've got imaginary arrows with an imaginary area. Supposing you decide to make the imaginary area not at 90 degrees to the arrows, then you've got to take into account a trig function. The way we deal with that is we say, okay, we're going to deal with a trig function by taking a normal, an area vector which is normal to the surface and has the size of the area. So if this is 3 square meters, that's a 3 square meter vector. If it's 5 square meters, it's a 5 square meter vector, whatever we like. And then we have our electric field vector. An electric field, we've got to distinguish between the electric field lines and the electric field vectors. If I remember this diagram down here, and I had these lines and they go from positive to negative, that's not an electric field vector. That's an electric field line. That's the path that would be followed by a positive charge if you released it at the beginning point. It would go to the end point. But if I want to know the electric field at any point, it is a vector which is a tangent to this line and has a length which is proportional to the size of the electric field. So just in our language, these are electric field lines here, but I can imagine an electric field vector associated with that line and an area vector associated with that one, and we do a dot product between the two. Okay. And so we did some examples of that, and then we got to about here. And what I'm going to do is I'm going to imagine making up an enclosed volume using these Gaussian cards, these little surfaces. And it doesn't matter what shape it is. They're not going to be potato shaped. They're going to be symmetrical when we actually do it for real. But in principle, it can be any shape. I just have an enclosed volume of space. And I'm just looking at one of the cards that make up this surface. So I'm looking at one of these little guys, and I'm saying, well, that little guy must have an area vector. Let's call it dA for little area. And there must be an electric field going through it, so we have our E. And so I can do my usual thing where I say my flux is equal to the electric field multiplied by the little area times the cosine of the angle between them, which is a dot product. And then you say, well, let's do that for every card on this surface. Let's just make a ton of cards on this surface. And we'll have, each one will have an electric field vector, and each one will have an area vector. Electric field could be 0, could be going in, could be coming out, whatever. And we say, well, then the total flux in or out, the net flux in or out, would be given by the limit as my little bit of area goes to 0 of this summation of all the little cards with their electric fields and their little bits of area. And that becomes a surface integral of EI dotted with dA, the area vector. Just summarize the whole thing. If you make these things small enough, you don't need to do a summation, you do an integration. There's 3 possibilities when you think about it. Either the electric field, so the first thing I've got to say is, we talked before about how do you know when you have a little card whether the area vector is pointing up or whether the area vector is pointing down. It could be either. We just said it's perpendicular to the surface, but which surface? The top surface or the bottom surface? And the rule we're going to have is that the surface is always the outside surface of any enclosed shape. So it's always pointing outwards. The area vector always points out. So I have an area vector pointing away, I have an area vector pointing away, and an area vector pointing away. And they're always at 90 degrees to the surface, and this is the green Gaussian surface, completely made up by me, it's just imagined by me, and I chose to make it a sphere, so I'm doing a line through it, and it's basically this circular bit. So there's my thing. And then I'm imagining the electric field just coming from the right, just coming from the left towards the right, just to give me some variety. So I have electric field. And what I notice is that for my E times dA times the cosine of the angle between, in this case, theta is greater than 90 degrees. In this case, theta equals 90 degrees. And in this case, theta is less than 90 degrees. Yeah. And so that affects the sign of my amount. If I have a field lines are entering, so this is the field lines are entering, and my area vector is always pointing outside, then what I get is a cosine theta is negative. So that's a negative flux. When the electric field line goes into my Gaussian surface, it's an arrow going in, and so we call that a negative flux. When it grazes the surface at 90 degrees, then the cosine theta equals 0, so there's no flux. The arrow does not enter. And when I have my field line coming out, I have an angle that's less than 90 degrees. So I have a positive cosine, which is positive flux. So you can look at any Gaussian surface, and if the field line is going in, that's going to be, when it's going in, that's going to be a negative. And when the field line's coming out, that's a positive flux line. Yep. So if I had this, if I had that, and I said positive and negative and positive, and I chose to draw my field line around there, then because all the field lines go outwards from this positive charge, because all the field lines are going outwards, they're leaving, I end up with positive flux going through this Gaussian surface. And if the arrows are going in, it's negative flux. So arrows coming out, positive flux, arrows going in, negative flux. So we have a sign convention for it. It's arbitrary, but once we do it, we've got to stick with it. What I want to do now is I want to devise Gauss's law. So I'm going to use some math to devise Gauss's law. You won't be asked to repeat this. You'll be asked to use Gauss's law, but I want to derive it. And so we're going to take a very simple case. I'm going to take this case of a charge, and I have a point of interest. My point of interest is like inside this square. It's on the surface of the sphere. So I have a charge, and I have a point of interest, and I decided to draw a Gaussian surface that was spherical and symmetrical about that charge. We're going to use symmetries a lot because it makes the math easier. There is a general relationship between the net flux through a closed surface, we call that the Gaussian surface, and the charge that it encloses. When E is parallel to dA, so let's look at our little box. Because I've made this radially symmetric, all my electric field lines are radial, aren't they? Yeah? And also all my dA lines are radial. Yeah? So if you think about it, E dot dA, their vectors, is equal to the magnitude of E times the magnitude of dA times the cosine of the angle between. Remember that from the definition of a dot product? Okay, if I make E parallel to dA, that makes cosine of 0, which is 1. So by making these guys parallel, I can get rid of the angular effect. It's equal to 1. It's not different for different bits of the Gaussian surface. It's always equal to 1 for this surface. So that's kind of nice, because E dot dA becomes E times dA. So I say my flux, which equals the surface integral of E dot dA, is equal to, well, it's going to equal E times dA. And actually, I'm going to change that. And there's a second little bit, which is the E is constant. And why is E constant on this Gaussian surface? What is it about this Gaussian surface's structure relative to the charge that tells me that the electric field is constant? It's stuck inside, but there's something more specific than that. It's inside, but it's in a special place inside. Think about a point charge and think about going to different positions away from the point charge. Is it a constant electric field as you go further and further away? No. Falls off, doesn't it?
Yeah, it's in the same position.
It's in the same distance. It's the same separation in all directions. Because I'm thinking about, E and dA and E and dA all over this thing. And it's the same distance. So that means that E can come out of, E becomes a constant. And so it can come out of the integral. So that's interesting. My flux, which equals my surface integral of E dot dA, becomes E times the integral of dA. Well, I know E. E is, from Coulomb's law, KE Q over R squared. Remember we did that in Coulomb's law? And we know that the surface area of a sphere is 4 pi R squared. So I can just substitute in. So I say, well, my flux, which is equal to the surface integral of E dot dA, which equals, and again, I wish I'd not done those two guys, is equal to E integral dA is equal to KEQ over R squared times 4 pi R squared. And the R squareds cancel, which is kind of nice. And we get 4 pi KE times the charge inside. So if you think about it, the number of arrows, if we think of the flux as the number of arrows, it's 4 times, which is a constant, times pi, which is a constant, times Coulomb's law, which is a constant, times whatever charge we have. Yeah? So let's say I have a 1 Coulomb charge. That will be 4 times 3.142 times 9 times 10 to the 9 times 1. That's how many arrows we should imagine. And that would be a lot. 12, 9 12s, 108, about 100, and it's about 1 times 10 to the 11 arrows for a 1 Coulomb charge. I'd be there all day drawing them, It's very fine detail. That's beside the point. That's beside the point. If I recall that KE, Coulomb's constant, is 1 over 4 pi epsilon naught, then flux is equal to the integral of E dot dA, which equals, well, now I have, instead of that KE, this is 4 pi. Instead of that KE, I got 1 over 4 pi epsilon naught times Q. And the 4 pi's cancel. I get Q over epsilon naught. Q is the amount of charge inside my Gaussian surface. So I get a very simple relationship between the amount of flux and the charge that's trapped inside. And that's kind of useful. It's the amount of charge divided by epsilon naught, which is a constant. Let's take a couple of examples. So here's three positives, all close together. Don't worry about the separation, close together. And they give me a radially symmetrical E field. And I chose to draw a Gaussian surface which is heart-shaped, just because. I just decided to draw a Gaussian surface which is heart-shaped, and I made that up. You can draw whatever Gaussian surface you like, but you've got to live with it. And so some are better than others. And I say, well, the net flux through any closed surface that surrounds a point charge Q is given by, well, my net flux is equal to Q inside over epsilon naught. So this is just, three positives over epsilon naught. Boom. Very straightforward. Let's say I move it so there's no Q inside. There's still the three charges, but they're not inside anymore. Then my net flux is equal to the charge inside my Gaussian surface over epsilon naught, which is 0 over epsilon naught. What would you get if you had a negative charge inside? You'd have a negative flux. Remember, this is telling you how many arrows are leaving or coming. If they're positive, they're leaving. If they're negative, they're coming. We can do this. We can say, okay, let's take Gaussian surface 1. That's the middle one. Well, that would be Q1. My flux equals Q1 over epsilon naught newtons per Coulomb meter squared. And if I take this one, it's, that's going to be Q2 plus Q3 over epsilon naught newtons per Coulomb meter squared. And this one, this is 0 newtons per Coulomb meter squared. And that one is Q1 plus Q2 plus Q3 over epsilon naught newtons per Coulomb meter squared. It's all there. Yeah? Very simple. So don't miss out on the visualization. Don't miss out on this bit because the next bit gets a bit involved. Just remember this. You just take the amount of charge inside and you divide it by epsilon naught. And in the test, you don't even have to know what epsilon naught is. You just put down epsilon naught. Epsilon is the Greek letter, like a curly E. And naught is English for 0. So in the States, sometimes they call it epsilon 0, but often they call it epsilon naught. N-A-N-O-U-G-H-T. N-A-U-G-H-T. Glad I left. It's like 0. It's just a number. A 2 Coulomb positive, 2 positive, sits at the center of a spherical Gaussian surface. At the center of a spherical Gaussian surface. Surface is 3-dimensional. I've only got a 2-dimensional page, so I'm going to draw it like that. The radius is 8 meters. What's the electric flux through the surface? The flux through the Gaussian surface is equal to, well, let's have a look. It was equal to the surface integral of E dot dA. Why do I write that down? Because I want to remember it. Which equals Q inside over epsilon naught. I'm not going to use the middle bit, but I might as well write it down so I never forget it. And my flux is equal to, my Q inside is plus 2 over my epsilon naught newtons per Coulomb meter squared. What about the 8 meters? Makes no difference. I could have that. And the answer would be the same. whatever charge is inside, whatever shape you decide to be the Gaussian surface, just take that charge, divide it by epsilon naught. That tells you how many arrows are entering or leaving or whatever. If it's positive, they're leaving. If it's negative, they're entering. Ooh, IJK. Let's think about this. 5 coulomb negative charge sits at this point in space. And then a cubic Gaussian surface, we're given the side of it, and we're given 2 opposite corners of it. This is just geometry. I'm not going to be doing anything fancy with my IJK. I'm just going to be visualizing. 2, 2, 2. So let's just draw our so there's my charge. And it's 5 negatives. And this is where I think those click pens come in handy. It's kind of useful not to get confused. So now we're going to draw a Gaussian surface. So let's make it a different color. And it's 4 meters on edge. One corner is at the origin. And then we have 4, that's one edge, and 4, that's another edge, and 4, that's another edge. Because it ends at plus 4, plus 4, plus 4. And plus 4, plus 4, plus 4 is there. So if I look at this thing, there's the front of it. And there's the side of it. And there's the top of it. And down here there's the, back side and back corner and all that. My flux is equal to the integral, surface integral of E dotted with dA, which equals my Q inside over epsilon naught. And let's have a look. What is my Q inside? Is this 5 coulombs negative inside the Gaussian surface, or is it outside the Gaussian surface? It's inside, isn't it? If you look at it from the side, if I kind of look at it from the side, this is 0 and that's 4, and that's 0 and that's 4, and that's 4, 4. And this one was at 0 and 2 and 0, 2. So it's definitely inside. So, then in that case it's minus 5 over epsilon naught Newton per coulomb meter squared. So I just add my IJKs to do what they're good at, which is defining 3-dimensional space. Didn't have to do anything fancy with them. It's just, hey, they're useful. Yeah.
So if the charge is outside the Gaussian surface, you have to do the integral?
No. You turn around and say it's Q inside over epsilon naught. And if it's outside the Gaussian surface, there's no charge inside. And so the answer is 0. So let's think about that. Let's try and visualize it. So there's my charge, and there's my Gaussian surface. And now, because it's a negative charge, all the arrows are going in like that. So there's a visualization of what we just discussed. Yeah? Let's put this in a circle so you know it's not the same thing. Can you notice how this arrow enters the Gaussian surface, but it also leaves? So that positive flux of 1 is cancelled out by that negative flux of 1. And here, again, that positive flux of 1 is cancelled out by that negative flux of 1. If I draw more arrows, whatever arrows I draw, they enter and leave, giving a net flux of 0. So if there's no charge inside, no flux. There probably is a whole bunch of arrows passing through, but no net flux. Yeah, cool. Good question. So, I'm not above giving you a question like that even. I'm not above that. It's like, these are, because it's, sometimes what I see is everybody's looking at the top of the trees and they're tripping over logs. And it's like, so it's, don't throw easy points away because he's only going to ask us hard questions. I try not to do that. But there are some questions that I want to let you know are going to come up, and one of these Gauss's law problems are going to come up, and I want you to do them very specifically. We're going to say, using Gauss's law to determine the electric field caused by a specific charge distribution. So if we say flux is equal to the surface integral of E dotted with dA, which equals Q inside over epsilon naught. That's what I derived. I can rearrange this and try and get E by itself and figure out what the electric field is. And what I find is I can use this technique for situations where Coulomb's law would be hard to use. Now again, I'm going to cheat. I'm not going to just close my eyes and do it like the general case. I'm going to pick more specific cases where there's a fair amount of symmetry, and I'm going to decide on the symmetry. So look at what we do is, so there's a bit of a cheat takes place here. It's tempting to think that you're going to have to invent Gaussian surfaces. And it turns out that there's a canon, there's a family of Gaussian surface problems that get asked. And once you've seen them, if you follow it, you're not like inventing the wheel. Now, is it an exhaustive group that we look at? It's pretty good. So don't, and it's varied. So don't feel like you did nothing in mastering this bit because you didn't invent it. Whoever invented it, Gauss probably, or somebody using Gauss's math techniques, whoever did it was really good. And we walk in their footsteps. But it's not like we're not doing anything, You're still climbing a mountain. You're just not making the trail, Fair enough. So the trick for us is being clever about which Gaussian surface we choose to use. And remember, the Gaussian surface is going to include your point of interest. So the only thing I can tell you is the point of interest will be somewhere on that Gaussian surface. It's got to be, otherwise you're doing the problem on the wrong bit. But beyond that, it depends upon the symmetries of the problem. And the things to look for is, try and look for Gaussian surfaces where the electric field is constant over the surface. Well, we did that before, really. We picked that spherically symmetrical Gaussian surface. And try to look for things where the dot product between the electric field and the area vector is basically parallel, so that you have the cosine of 1. Or if you can't do cosine of 1, go the other way and try and get it where they're perpendicular, so you get the cosine of 90. Not cosine of 1, the cosine of 0, which is 1, or the cosine of 90, which is 0. But you don't want in between. It's like the general case sucks. You want nice symmetries. And then, okay, the other alternative is try and pick a Gaussian surface where you can argue that the electric field is 0, because if it's E dot dA and E 0, you can forget about it. So those are the things I try and do. And there's a few different examples. So we're going to start off with the first one that we did. We're going to reverse our derivation. So we derived Gauss's law using this scenario. Now we're going to use Gauss's law to prove this scenario. Well, it's a circular argument, really. This does not prove anything, but But imagine I say to you, all right, there's a point source of charge, and there's a point P, which is some distance away, and I want you to find me the electric field at that point P. So what you'd do is you'd say, well, okay, I got to put a Gaussian surface through this point P, and I've drawn this somewhat three-dimensionally. You know, if there's Q, there's my P, and then my electric field is like that, and my area vector is like that. So I'm drawing this kind of like three-dimensionally up here. That's why there's squares inside, you know. And what I can say is, well, we picked a spherical Gaussian surface centered on a point of charge because, and I can say, well, for every little point on this surface, the electric field is parallel to the area vector. They're both radially symmetrical. So for every point, the electric field is parallel to the area vector. And so my E dot dA equals E times dA cosine theta, which equals the magnitude of E times the magnitude of dA. So that which is complicated becomes simple. And then secondly, E is constant on this surface because we're always the same distance away from the charge. So I can take the E outside. So I'd love it, and I'll show you this in a minute, where you write down those two steps. I really want to see those two steps. Because I'm interested in the physics of how we do calculus, not the calculus of how we do calculus. The trade-off is, I give you simple calculus to do, really. You don't get error functions and all that kind of nonsense. But I want the justification for the steps. And so E, well, my integral dA, I know it's 4 pi r squared because it's a sphere. So rearrange. E is equal to Q in over 4 pi r squared times epsilon naught. Oh, KE is equal to 1 over 4 pi epsilon naught. Oh, E is equal to KE, Q inside, over r squared. Remember, how can I do this? I can say my epsilon naught equals 1 over 4 pi KE, and then substitute that in there. So that equals Q inside over 4 pi r squared times epsilon naught, 1 over 4 pi KE, which equals Q inside, that KE goes on top, over r squared is left. So there's a couple of steps in that little step. There's a couple of steps there, but they make sense. Okay? That's how you do these. Let's step through it one more time. Let's do it together. 10 coulomb positive charge is located at the origin. Let's draw a little origin. 10 positive. Using the method of Gauss's law as shown in physics class, I'm actually going to say physics class on the test rather than class, because you could say math class. Physics class. Determine the electric field at any point 3 meters from the point charge. I'm going to put my P there on the x-axis. It doesn't say anything about I can't. And for me, so that I got a tendency to get confused. So I'm going to, I don't know if you can see the different color, but I'm going to use a different color. Purple. And let's have a look. I'll call this guy here. I'm just going to step ahead a little bit. I want to just see some nomenclature here. Yep. I'm going to call this R, just for the sake of it. R is the distance from the center of my Gaussian surface to my surface, and the center of my Gaussian surface is superimposed on the charge. Yep. So I say, okay. Imagine my little surface. There's my E. And there's my dA. And I could have done that all over. It's the same all over. And I say, well, my flux is equal to the surface integral of E dotted dA. They're both vectors, which equals Q inside over epsilon naught. So the first thing I want to look for is, do you write down Gauss's law? Because I want to see, it says, using the method of Gauss's law, I expect to see Gauss's law there. And then I say, oh yeah, E is parallel to dA on Gaussian surface. So my flux is equal to the integral of E times dA, which equals Q inside over epsilon naught. Yeah? Then the next thing I want is E is constant on Gaussian surface. So my flux is equal to E times the integral of dA, which equals Qn over epsilon naught. Yeah, because it's constant, I can take it out of my integral. Only constant because I'm using a symmetrical sphere. If I had the sphere over to one side, it won't work. So then I say, oh, integral of dA, in this case, is equal to 4 pi r squared, because it's a sphere. So flux is equal to E times 4 pi r squared, which equals to Qn over epsilon naught. So now I can rearrange. So E, don't worry about flux anymore, it served its purpose. E is equal to Qn over 4 pi r squared times epsilon naught. And if I remember, oh, Ke is equal to 1 over 4 pi epsilon naught, which gives that epsilon naught is equal to 1 over 4 pi Ke. So E is equal to Qn over 4 pi r squared 1 over 4 pi Ke, which equals Qn over, Ke Qn over r squared, which equals 9 times 10 to the 9 times plus 10 over, what do I say that, 3 squared, which equals 1 times 10 to the 10 newtons per coulomb meter squared. By the way, that's a lot of that's a lot of flux. That's a lot of electric field. Pardon?
Squared right there, right? Not 32?
Oh, that's 3 squared, yeah.
Sorry.
No, you're good, good. So that would drive me crazy when I was a student. I'd not ask, and I'd go home, and I'd think it was 32, and I'd go, where does 32 come from?
I was thinking, where do you get that?
And I'd go, eventually after 2 hours, I'd go down and see my buddy Ted, who would just like cross it out and put 3 squared, and he'd go, spelling mistakes, Tony, that's spelling mistakes. And I spent 2 hours on that. He goes, yeah, you got to spot those spelling mistakes. And sometimes it was that I made a mistake writing it down, and sometimes it was the actual thing was written down was wrong. So it goes just to finish off the sermon, the difference is Ted had confidence in himself. And if he couldn't follow it, he checked to see there was a mistake. Whereas I did not. I assumed it was all me. And so I burned through time thinking that I'd done something wrong. So you've got to have a bit of confidence in yourself. You've got to earn your confidence, but, you know, check to see it's not a mistake. It's not bad. We knew the answer. It's like, I could have used the equation to begin with. So it's like, you know, ho-hum, you know, who cares? But now I'm going to show you ways where it's not. We don't know the answer. And the first one is we have a ball of charge. And for a ball of charge, there's two questions I can ask. What's the electric field outside the ball of charge? But also, probably more interesting, what's the electric field inside the ball of charge? We look at the answers. This is our same old, same old. It doesn't matter if it's a point of charge or a ball of charge if you're on the outside of it. Remember what we do in mechanics? We take all the mass and we assume it's at the center of mass to make our problems easier. We took the whole Earth and assumed that all the mass was at the center of the Earth. Well, we can do the same thing. We can take all that charge and assume that all the charge is at the center, as long as we're only interested in points outside. How would I do this using Gauss's law? Same as normal. Just at the end, I'd say, oh, Q inside is whatever that charge is. This second one is a bit more interesting. You can see that it's not the same answer. Which is the variable? Is R the variable? Or is A the variable? When we well, actually, neither one of them. When I think about it like that, I mean, it's like it depends on me. But for a given ball of charge, I can put you at different values of R. So R is the variable for a given ball of charge. Can you see how if I plot a graph of E versus R, and there's my A. Let's put the A on the line. There's my A. Can you see how outside I get an inverse square relationship? Because it's something over R squared. As R changes, my value of E, as R changes, my value of E changes in an inverse square relationship. Yeah. Can you see how on the inside, as R changes, my E goes through a linear relationship, starting off when R 0, E 0. So at the very center, there is no electric field. And as I go further and further towards the outside of this ball of charge, there's more and more and more electric field, until I get to the surface when there's the maximum electric field. And then as I go further away, I have an inverse square law from the center, not from the surface, but from the center. And that's just like gravity, isn't it? If you go above the surface of the Earth, little g falls off in an inverse square relationship. If you go inside the Earth, little g gets less. If you could drill a hole from here to Australia, you'd find that as you fell towards the middle, the pull of gravity would become less and less and less. When you're at the middle, there's no pull of gravity. When you go outwards, there's more and more pull of gravity until you get to the surface on the other side. So it's a kind of funny pendulum. Let's do some work with this. Using the method Gauss's law that was shown in class, determine the electric field 2 meters from the center of a 4-meter radius. So let's draw this. So the first thing I'm going to do is I'm going to be careful with the color of my pens. I'm going to do my charge in red. So here's my, and I'm going to call this A. I'm not going to call it R. It's the radius of the charge. I'm going to call this A. And then I'm going to go here, and I'm going to have a purple color. And that's R. And this is my Gaussian surface. And I chose to make that Gaussian surface symmetrical with this ball of charge because life is much nicer when I do that. And I can picture my point of interest. There's my point of interest. And there's my electric field. And there's my little bit of area. And I say my flux is equal to the surface integral of E dotted with dA. And that equals my Q inside over epsilon naught. And what's the next thing I say? I look at my point of interest, and what's the next thing I say? Ah, yes, I say E is parallel to dA. I should say vector E is parallel to vector dA on the Gaussian surface. So my flux is equal to the surface integral of the magnitude of E times the magnitude of dA, which equals Q inside over epsilon naught. And what's the next thing I say now? E is constant. The magnitude of E is constant on Gaussian surface. Is the vector E constant on the Gaussian surface? No, because it points in different directions. So it actually is the magnitude that is constant. So now I say, well, my flux is equal to E surface integral dA, which equals Q inside over epsilon. Oh my word, this is getting so boring because it's what we did last time. The integral of dA is equal to 4 pi r squared. And it is r. Let's just stop for a minute. It is r because it is the surface of my Gaussian surface. It is not the surface of the ball of charge. And people make that mistake. So in that case then, my flux is equal to E times 4 pi r squared, which equals Q inside over epsilon naught. So let's just do a bit of bookkeeping here to keep everything nice and neat. So now E is equal to Q inside over 4 pi r squared times epsilon naught. Oh man, this is just like the same old, same old. And of course, Ke is equal to 1 over 4 pi epsilon naught. So that gives me that E is equal to the Q inside over Ke times the Q inside over r squared. Well, that was a waste of time. I just did exactly what I did before. But it's not the same answer. I don't understand. It's not the same answer. It's a different answer on the right-hand side. Oh! What is the value of Q in? Oh, man. Oh, I got to apologize, like, incredibly profusely. No, I got to apologize incredibly profusely because what I've done is I've drawn the wrong writing diagram. So let me just So we're back, and I redrew this diagram because I just drew the wrong diagram. My Gaussian surface, the purple bit, is inside the ball of charge. And so the question I was asking was, the math is all okay. The question I was asking was, oh, so what is Q inside? And it's tempting to say it's 9 coulombs. But the whole ball of charge is 9 coulombs. So it's the amount of charge inside the Gaussian surface. It's not Q inside the charge ball, it's Q inside the Gaussian surface. So I say, well, my Q inside is equal to my little volume multiplied by my volume charge density. So my Q inside is equal to, well, the little volume is going to be 4/3 pi r cubed, and it's little r because it's to the Gaussian surface. And my volume charge density is big Q over the big sphere, which is 4/3 pi a cubed. So my Q inside is equal to the 4/3 pi goes away. It's going to be Q times r cubed over a cubed. Now let's just look at that and just think for a minute. If r is less than a, r cubed over a cubed is less than 1. Less than 1 times q is a smaller amount of charge. If you have them upside down, if you get your a and your r confused, you get a bigger amount of charge than is actually in your ball. So you've got to watch out for that. But there's a little insight there. And then we say, well, E is equal to KE. And rather than Q inside, I'm going to say big Q R cubed over A cubed. And that is all divided by R squared, which equals KE big Q R over A cubed. And that's where that expression comes from. A cubed stays on the bottom, that cancels with that. So this equals, let's leave KE in. KE, the Q is plus 9. The R is to the Gaussian surface, and it's 2 meters from, so that's 2 over the A cubed. The A cubed is the size of the actual ball of charge, which is 4 cubed. So E is equal to 18 over 64 KE, which equals 9 over 32 KE newtons per coulomb meters squared. So, it's the same beginning, but we have to recognize that the amount of charge inside our Gaussian surface is different from the amount of charge outside our Gaussian surface. And, you know, can you see how making sure that we know our geometrical shapes means that you don't have to be scratching your head saying 4/3 pi r cubed. It's just ingrained, you know it. It's just there at your fingertips whenever you need it. So it's just, it makes that whole thing a bit simpler. The big mistake, and I'll be honest, so this is a possible test question, and I want to see, you know, I want to see that bit, and I want to see a good diagram, and I want to see these justifications, and I want to see the fact, you know, the surface area is 4 pi r squared, and I want to see that you know how to get the amount of charge inside, and I want to, you know, I want to see all of it. And I'll tell you that something, this or a couple of other questions are possible, but one of them is going to come up. And what happens is people, they learn the answer. They learn the KEQ R over A cubed, and there's nothing wrong with that. But then what they'll do is they'll kind of put down Coulomb's law and they'll work forward and get lost. And they'll put down the answer and work backwards and get lost, and there's no middle bit. And that burns me so badly because I just wasted 20 minutes checking your math. And if I could, I would take points away. I'd say, thank you, here's -5 for just like, you know. Occasionally somebody puts down a smiley face and they say, I just don't remember it. And I feel like giving them extra points. I can't, but I feel like giving them extra points. And occasionally what will happen is people get right to the very end and then they're just not thinking and they'll get the A and the R confused because the diagram's not good. And they'll end up with an electric field that's bigger than it should be rather than smaller than it should be. So watch out for that. Pardon?
Not like how you would have with your bad diagram.
No, I had a bad diagram with the right math. But yeah, it's like slips happen like that. So, you know, the more you write down, the more I can say, well, they got that bit and they got that bit and they got that bit. So I can spot it. And I don't mind. It's not that, I'm not saying I don't want to grade your stuff. It's just, I want to grade your stuff when there's an earnest effort, not when you're trying to hide the fact that, you know. I don't know what I'd do if I was a student and I was in that position. I don't know what I'd do. Would I try and finagle? I suppose you could finagle your way back and maybe hope to join in the middle. Yeah, I don't know what I'd do, but don't. Okay. But not so bad. It's the same old, same old. So this is the next one of interest. I've only got a couple of minutes, but I want to point something out about this. You do the same old, and you say, what's the charge inside? And the charge inside is whatever Q is. Yeah, whatever the Q is on the shell. So outside, it's the same old, which is a bit trivial. Inside, if I give you this same inside, you're going to do the same thing, but now you're going to say Q inside equals 0. So it's not that the inside is any less. It's just that these two, there's no variable bit. If you're outside, it's an inverse square law. If you're inside, it's 0. Because there's no, inside this Gaussian surface, there's no charge. So there's no electric field.
Oh, so is the charge the shell?
The charge is this shell, yes. Yeah, the Gaussian, I'm trying to be complete with my Gaussian surfaces, I'm trying to keep as blue shapes. So the greeny blue shell is where all the charge is, and the blue shape is my Gaussian surface. Just have I got time for this? So if I was to plot a graph of this where I had electric field versus position, when I'm outside it's the same old, it's the inverse square. But inside, it's 0. There's not this sloping line. It's 0 until you get to that point. I'm not above asking you for this diagram as well. Think about if this was the case with the Earth. We could dig a hole through the crust of the Earth and we could open a trapdoor. And inside that shell of the Earth, there'd be no pull of gravity. You wouldn't fall into the middle. You would float. It would be like being underwater, just floating around anywhere inside the shell of the Earth.